beneath the Pacific Ocean's surface, off the rugged coast of Oregon, sits a volcano most people have never heard of. It doesn't tower over cities or loom on the horizon like Mount St. Helens. In fact, you'd never see it unless you traveled hundreds of miles offshore and descended into the deep ocean. Yet to scientists, Axial Seamount is one of the most important and closely watched volcanoes in the world. Why? Because unlike most volcanoes, Axial has a predictable rhythm. It erupts on a timetable roughly every decade, and according to the latest data, its clock may be ticking down toward another eruption before the end of 2025. Axial Seamount lies on the Juan de Fuca Ridge, a tectonic spreading center about 250 miles west of Oregon. This ridge is where two massive plates of Earth's crust are pulling apart, allowing magma to rise from the mantle and create new oceanic crust. It's a slow but constant process, one of the ways the Earth recycles itself. The volcano itself is huge. It rises about 3,600 feet above the surrounding seafloor and spans roughly 15 miles across, large enough to be considered a true seamount rather than a small vent. Its summit caldera, a crater-like depression, stretches about 2.5 miles wide and 5 miles long. For comparison, that's nearly the size of Manhattan. Axial Seamount isn't just large, it's active. Since scientists began studying it in the late 20th century, they've confirmed eruptions in 1998, 2011, and 2015. Each time, the volcano released flows of lava across the seafloor, reshaping the terrain and covering several square miles. The 2015 eruption was particularly significant. Lava flows up to 400 feet thick spilled out, altering hydrothermal vents and burying instruments that scientists had placed on the seafloor. That eruption also confirmed something researchers had suspected. Axial could be predicted. Prior to 2015, instruments showed the seafloor inflating, rising steadily, before suddenly dropping as magma was released. By comparing those cycles, volcanologists realized they could forecast the next eruption with surprising accuracy. That's what makes Axial unique. While predicting eruptions on land remains one of science's toughest challenges, this underwater volcano has provided a rare, almost clock-like record of behavior. Axial is sometimes called the best monitored volcano in the world. That's because it sits directly under part of the Ocean Observatories Initiative, a seafloor cable network that transmits data in real time. Through this system, scientists monitor seafloor movement. Instruments track how much the ground swells or sinks as magma shifts. Seismic activity. Sensitive seismometers detect earthquakes, often triggered when magma cracks surrounding rock. Hydrothermal activity. Sensors record changes in hot, mineral-rich fluids venting from the seafloor. Together, this data offers an unprecedented look at the inner workings of a volcano. It's like having a stethoscope pressed against Earth's heartbeat. In 2025, Axial is once again showing all the signs of an approaching eruption. The seafloor at the summit has been inflating like a balloon, rising more than 2 meters since the 2015 eruption. This inflation occurs as magma pushes into chambers beneath the crust, forcing the seafloor upward. In addition, seismic activity has surged. In late August, researchers recorded over 2,000 earthquakes in a single day. Most were tiny, but their sheer number suggests that magma is moving and stressing the crust above it. In past eruption cycles, similar swarms of quakes occurred just before lava broke through. At first glance, a deep ocean eruption may not sound like a big deal. Unlike Mount St. Helens in 1980, or the 2022 Hunga Tonga Hunga Ha'apai eruption in the South Pacific, Axial's eruptions don't blast ash into the sky. or endanger cities. The water pressure at that depth suppresses explosions, and lava flows quietly across the seafloor. But there are several reasons why axial matters. Each eruption provides a natural laboratory for studying how magma systems evolve, how seafloor crust fractures, and how ecosystems respond to sudden change. If scientists can successfully forecast Axial's next eruption, it would mark one of the first reliable volcanic predictions in history, a breakthrough that could one day apply to land-based volcanoes. Most of Earth's volcanic activity occurs under the ocean, along spreading centers like the Juan de Fuca Ridge. By studying Axial, researchers learn more about the forces that constantly reshape our planet. Axial isn't isolated. It's part of the Pacific Ring of Fire, the vast arc of seismic and volcanic activity circling the Pacific Ocean. But while many of those volcanoes sit on land and pose hazards to millions of people, Axial represents a quieter, hidden side of volcanism. Its eruptions remind us that much of Earth's activity occurs far below the waves, shaping the planet in ways we rarely notice. Scientists learned just how valuable Axial's monitoring network was during the 2015 eruption. The pressure sensors on the seafloor had been recording steady inflation for years, then suddenly dropped as magma drained from beneath the summit. The deflation coincided precisely with the eruption, confirming that Axial's breathing cycle, swell, then collapse, could be used to anticipate future events. In fact, the 2015 eruption had been predicted within a 2-year window, one of the most accurate volcanic forecasts ever achieved. This predictive ability comes from the unique array of instruments on Axial's summit, all tied into the Ocean Observatories Initiative. The backbone of that system is a fiber optic cable stretching from the coast of Oregon to the volcano itself, nearly 250 miles offshore. That cable powers dozens of sensors and streams their data back to shore in real time. Unlike most submarine volcanoes, which are studied only when research ships visit, Axial broadcasts its activity around the clock. The equipment includes highly sensitive seafloor pressure sensors capable of detecting vertical changes of just a few millimeters. When magma pushes upward, the seafloor inflates, and the sensors register the rise. Since 2015, they've measured more than 2 meters of uplift, evidence that the magma chamber beneath Axial is filling rapidly. Seismometers pick up the earthquakes triggered as molten rock cracks its way through the crust. During quiet times, Axial records a handful of quakes per day. But when it grows restless, swarms numbering in the thousands can erupt within 24 hours. One such swarm struck in August 2025, when more than 2,000 quakes rattled the volcano in a single day. Other devices monitor tilt, measuring tiny shifts in slope as the ground bulges. Chemical sensors track the hydrothermal vents that spew scalding mineral-laden water from the summit. These vents can change abruptly during eruptions, when new lava flows alter the plumbing beneath the seafloor. Cameras provide visual confirmation, capturing the aftermath when fresh lava hardens into new crust. Together, these instruments give scientists an unparalleled view of a volcano's inner workings. That view has revealed that Axial behaves more like a pressure cooker than a stick of dynamite. Instead of violent explosions, it tends to release magma gradually, allowing lava to flow quietly across the deep ocean floor. In 2015, lava covered several square miles, in places piling up hundreds of feet thick. Instruments deployed on the seafloor were engulfed and destroyed, but many continued transmitting until the moment they were buried, offering extraordinary data about the eruption's progress. Even though Axial's eruptions don't threaten human settlements, they matter for several reasons. For one, they reshape the seafloor dramatically. Hydrothermal vents can be wiped out overnight, extinguishing entire communities of organisms that rely on their chemical energy. Yet just as quickly, new vents open and are colonized by bacteria, tube worms, and other species adapted to life in the dark. Each eruption becomes an experiment in how ecosystems collapse and recover, giving biologists rare insight into the resilience of life in extreme environments. For volcanologists, Axial is proof that eruptions can, in some cases, be forecast with remarkable precision. On land, prediction remains notoriously difficult. Even when magma is rising, it's hard to know whether it will actually erupt or stall beneath the surface. Communities living near dangerous volcanoes like Vesuvius in Italy or Merapi in Indonesia face uncertainty every time activity increases. By studying Axial's reliable cycles, researchers hope to refine their models and improve forecasting worldwide. The seamount is also a window into the fundamental processes that build Earth's crust. Most volcanic activity on the planet happens underwater, along mid-ocean ridges where plates are pulling apart. These eruptions create vast amounts of new seafloor, constantly renewing the ocean basins. Yet because they happen in such inaccessible places, they're rarely observed directly. Axial is the exception, a mid-ocean ridge volcano that scientists can watch almost as easily as if it were on land. The current signs of unrest fit the familiar pattern. Inflation has reached levels comparable to those observed before the 1998, 2011, and 2015 eruptions. Earthquake swarms are becoming more frequent and intense, suggesting that magma is forcing its way upward. Hydrothermal vents are showing subtle chemical changes, another indication that molten rock is on the move. Many researchers believe the volcano is primed for another eruption, with odds highest before the end of 2025. If that happens, the event will likely play out much like past eruptions. The seafloor will abruptly drop as magma drains from beneath the summit. Lava will spread across the caldera floor and surrounding slopes, burying some instruments but sparing others. Hydrothermal systems will be rearranged, with old vents smothered and new ones springing to life. Within weeks, research ships will arrive to map the fresh flows, recover surviving instruments, and deploy replacements. And once again, scientists will compare the data to previous cycles, refining their understanding of how Axial works. While the eruption itself may remain invisible to anyone on the surface, its importance cannot be overstated. Axial offers a rare chance to test predictions in real time. Each cycle that ends in a confirmed eruption strengthens the case that careful monitoring can indeed provide accurate warnings. For a field that has long struggled with uncertainty, that lesson alone makes Axial one of the most valuable volcanoes on the planet. When Axial erupts again, the scene will be violent up close, but almost invisible from the surface. At nearly a mile deep, the enormous pressure of the ocean prevents explosive blasts. Instead, molten lava will push through fissures in the seafloor, spreading in long fluid flows. In 2015, some of those flows were hundreds of feet thick, covering nearly 8 square miles. This time, the scale could be similar or even greater, depending on how much magma has built up in the chamber. One of the most immediate effects will be the destruction of existing hydrothermal vents. These vents are like underwater geysers, spewing superheated mineral-rich water into the cold ocean. Entire ecosystems cling to them. Colonies of bacteria that thrive without sunlight, tube worms that rely on those microbes, and shrimp and crabs uniquely adapted to the extreme environment. When fresh lava covers the vents, those communities are wiped out in an instant. But just as quickly, new vents form along cracks in the cooling rock, and new life moves in. Each eruption resets the system, giving biologists a living laboratory for studying resilience and evolution in extreme conditions. Beyond the biology, the geology itself is critical. Submarine eruptions account for most of the new crust formed on Earth each year, yet they remain some of the least observed processes on the planet. Every time Axial erupts, it adds another chapter to the story of how the seafloor is created and reshaped. Mapping the new terrain after the eruption will show exactly how much lava was released, how the caldera collapsed, and how the ridge system evolves over time. This data helps refine models of crustal growth, not just at Axial, but at mid-ocean ridges around the world. The eruption will also provide a rare test of volcanic prediction. For years, scientists have pointed to Axial as the best candidate for proving that eruptions can be forecast with confidence. The steady inflation of the seafloor, the swarms of tiny earthquakes, the chemistry of hydrothermal fluids, all of these signals are lining up in ways that match the patterns before 1998, 2011, and 2015. If the volcano does erupt before the end of 2025, as many expect, it will validate years of monitoring and confirm that Axial truly runs on a cycle. That confirmation would ripple far beyond the seafloor. It would strengthen efforts to apply similar techniques at land-based volcanoes, where reliable forecasts could save thousands of lives. While the risks from Axial itself are minimal, too deep to trigger significant tsunamis, too far offshore to threaten coastal cities, the scientific opportunities are enormous. The Ocean Observatories Initiative ensures that instruments will capture every stage of the eruption in real time. Ships and remotely operated vehicles are already standing by to revisit the site after the event, to map the fresh lava and recover instruments that survived. For scientists, it's the rarest of chances to watch a volcano erupt not in hindsight, but as it happens, with a flood of live data. There are even broader implications. Hydrothermal vents created by eruptions like axials are thought to be potential origins of life on Earth. Chemical reactions in these extreme environments may have produced the first building blocks of biology billions of years ago. By studying how vents are destroyed and reborn, researchers get glimpses of the processes that may have sparked life itself. Some see Axial as an analog for environments on icy moons like Jupiter's Europa or Saturn's Enceladus, where under-ice oceans could host similar volcanic and hydrothermal systems. Watching Axial erupt may help guide future missions searching for life beyond Earth. For geophysicists, the lessons reach deeper still. Understanding how magma accumulates and releases beneath axial sheds light on the mechanics of all volcanoes. Why do some eruptions build pressure slowly, while others erupt catastrophically? How does the crust fracture and heal? What controls whether magma stays underground or breaks through to the surface? Each eruption at Axial adds new data points to these questions, helping unravel the mysteries of Earth's engine. And then there's the simple reality of change. The next eruption will erase parts of the landscape that scientists have been studying for a decade. Instruments will be entombed in lava, hydrothermal vents will vanish, and seafloor features will disappear. In their place will be fresh terrain, raw and new, waiting to be mapped. It is a reminder that the seafloor is not static, but alive, constantly reshaped by forces far beyond human control. What makes Axial so compelling is that it allows us to witness this process on a human timescale. Most volcanoes erupt unpredictably, separated by centuries or millennia. But Axial's clock-like rhythm means that within the span of a single career, scientists can observe multiple eruptions and piece together the cycle from beginning to end. It is as close to a controlled experiment as nature ever provides. The world's attention may be on land-based hazards, tornadoes, hurricanes, earthquakes, but beneath the Pacific, this hidden giant is preparing to write its next chapter. When it does, it won't bring devastation to cities or skies darkened with ash. Instead, it will quietly redraw the seafloor, transform ecosystems, and send back data that may one day help predict eruptions in places where lives are at stake. And for scientists watching their instruments tick upward, quake by quake, that moment may be just around the corner.